Alors bonjour, je me présente, je suis Sarah, je suis data scientist chez Data Scientist depuis janvier. Aujourd'hui, je vais vous présenter un data atelier sur la Multibox Detection. On va attendre que les gens se joignent à nous. Entre-temps, je vais vous parler un petit peu du fait que on propose chez Data Scientist des formations en data analysis, en data science, en deep learning et bien d'autres technologies associées aux data et à la mise en production de données. Aujourd'hui, l'atelier qu'on va faire, c'est un atelier qui va être essentiellement dirigé vers les data scientists. C'est une problématique de deep learning qui va être prise sous l'angle de la facilité, on va dire ça comme ça. C'est-à-dire que je vais présenter en fait des structures qui sont nécessaires à la mise en place d'un certain nombre d'outils, mais qui sont la partie en fait très simple de la mise en place, mais qui peut poser des problèmes puisque certains de mes élèves ont eu des problèmes associés à ce sujet-là. Ce que je vais vous expliquer, ça va être aussi une partie d'exemples et d'exemples d'utilisation, plutôt une partie de culture, des choses qui pourraient vous intéresser aussi en tant que simplement spectateur de ce genre de problématique. Euh, voilà, alors on va attendre encore quelques petites minutes. Euh, et euh, Si vous voulez avoir aussi d'autres possibilités de voir des vidéos sur la chaîne YouTube de Data Scientist, vous avez de super vidéos sur d'autres types d'ateliers qui pourraient intéresser aussi bien les data analysts que les personnes qui font du deep learning ou des PM ou des DevOps. Vous avez des cours qui sont de très bons cours et pas simplement des introductions. On a aussi un podcast. Je vous donnerai pas toute l'adresse ici, mais qui existe aussi et qui est un très bon podcast sur avec des interviews de personnes qui travaillent dans le monde du data. Voilà, donc on va commencer. Je vais vous présenter, c'est un data atelier qui va durer 45 minutes, 1 heure, sur des slides essentiellement et qui vont être très parlants et très visuels. Voilà. Donc, la multibox détection, qu'est-ce que c'est? En fait, c'est juste de la détection d'objets. De la détection d'objets simple, c'est-à-dire voir sur une image si vous avez un objet ou pas, et puis tracer une. Guys, I'm sorry. I started the data atelier in French and I forgot that it was in English. So I'm going to redo this all again because I had a long conversation before we started and it will not remain in French. I'm happy that the French people had the right introduction, but it's going to be very much easier for me right now. So the idea is that I wanted to introduce data scientists, that we're making bootcamp and long-term training on data analysis, on data science, on operation developments, and in MLOps as well. And that we will be presenting a workshop or a data atelier today that is a workshop on multibox detection. That is a subject that is mostly oriented towards data scientists, but some of it might interest those who want to learn more about the applications of deep learning and real life applications of data science. Uh, this will be a workshop on a very simple subject, or no, actually, it will be a simple aggregation of solving little issues on a problem of detection. So, knowing that multibox detection is a problematic on deep learning, and we'll go through a bit of the code, but not too much. We'll specifically try to tackle some issues that are related to what my students had to overcome when they were making their projects. And this actually is a an issue that a lot of people might try and find when you're starting as a data scientist, or you're building your first models, or you're working on your first projects. So now, what is multi-box detection? Multi-box detection is a simple object detection. You have object detection that is only looking at an image and knowing whether you have an object or not, and you can also draw a box around these objects. There is also a part where you have a picture and you have several objects on it. You have objects of different classes and you have objects of the same class, and you have to know whether you can draw the box around these objects. If your algorithm can get the multiple boxes around your objects. So what we're going to be talking about is an introduction, use cases of box detection, a simple implementation. We'll then talk about TensorFlow rapidly, which is a tool that will be used in order to process these calculations. We're going to talk then about how to tackle the grid that will enable us to make multi-box detection instead of just one box detection. Then we'll talk about generators, which are an object that can enable us to load our data sets in batches in order to be able to use the full data set without having or running on problems of memory. And we'll have also the evolution, that are other techniques that can detect objects in different ways, and we'll finally conclude on our problem. So what about introduction on our use cases? You can make a simple object detection on fruits if you want, with a simple on a simple project in order to train your skills. But you could also use a face recognition algorithm for sorting your pictures on Google Photo. And do that automatically, and the face detection part and the classification would be a use case for object detection that is actually implemented in real life tools, that is Google Photos. So if you look at this, we would actually detect the the boxes around the objects, or we would detect the objects around and create the boxes around these objects, and we would also classify as classes that we already know. So that's the Big Bang Theory. So that would be Leonard, Sheldon, Howard, and Penny, and Raj. But you could also do this on Google Photo with your family. So that's my family. And you would be able to click on one of these elements and get all the pictures from your data set, from your pictures that have the face of this beloved person. Now, we're going to also see that we can use remote sensing or satellite imagery in these problematics. So for instance, here, there's a way for you to look at the different objects from a aerial view, a tennis court, a pool, a factory, cars, but you could also see boats in the ocean, and you could use remote sensing images that are these ones that could present to you the objects that or detect the objects that you're looking for on an image. Uh, I guess that's it. Then you have real-time issues. Real-time is you have a streaming of data, a stream of images in a video, for instance, and you're trying to get a box around your objects throughout the video, so throughout the whole streaming. This is a problem that is actually interesting because you have to make a prediction that is accurate and that has to be made very fast with a lot of data. This is, for instance, for face recognition for security purposes. If you want to look or follow the workers that you have in a factory in order to be able to identify them and be sure that when they're making their work, two, there are no security breach in the factory. This might actually be interesting, not just in factory, but in data centers where the security is heightened and you don't want anyone that is not in your data center to enter there. What about the car recognition for self-driving cars? So here, supposedly my slides should be moving. I'm actually, this is a GIF and a video. Sorry, this is not. Uh, Let me just try to look. This was unexpected. These slides should be moving, so there might be a way for me to get more elements here. Um, so present. I'm sorry, I'm going to have to share my screen. So I'm going to be sharing my screen, and this will be done in a minute. Multibox detection. We're going to share this screen where we're going to have a better view of these elements. So this is going to be the boxes, the multi-boxes problem around self-driving cars. We're on the road and we're drawing the boxes, or we're detecting the cars that we have on the road. Here you have two boxes, and here you have the entire trajectory. So cut me if you don't see this, because I am not sure whether you can see this as I put this as a slideshow on the whole screen. If anyone wants to answer on the chat, that would be great. Otherwise, I will go on, considering that you guys see that. All right, so I consider that you guys see that, and we can put the slideshow on. And we can see this scene where you're in the street and you're driving your self-driving car, or the self-driving car is driving itself, and we have a lot of different objects that are recognized by the algorithm in a very, very short time. We have the pedestrian, the cars, and also the road signs that you also have to interpret and modify the trajectory of the car according to the diverse trajectories and distances that you've predicted also for your object. So you imagine that these algorithms are actually something that are very powerful. Now, I think you might also have, you might also have a joint detection for construction works or defense. So if you're on a roadworks or an extensive work, for instance, for an airport, and you want to track your tools or your cars or any of your projects, you probably can add you can add an object detection through drone images, for instance, and follow your workers or follow your cars. That is actually a very useful application. There's also the possibility to do that for defense, and I didn't put slides because I thought this was a difficult issue, but there's a way for you to send drones in warfare and follow the train follow people, basically. You can follow people, you can track activities and different objects, and this is actually a very let's say complex ethical issue. There's also a drone object detection for instance, plastic marine wastes, or as of general, environmental protection. So there's a great video that I found that is a diver who's actually looking at the plastic bags in the ocean, and in order to create, for instance, a vessel that would get the plastic on the plastic continent instead of getting fish. This is a very useful application of data science and multi-box detection and deep learning as of general. Now, you also have the possibility to do object detection and classification between cardboard and plastic in a recycle factory, or or detect uh, detect fires through satellite imagery. And these are actually existing firms, Recycli and also Aurora Technology. That's why I put them on your slides. So you see where the algorithm lies in the diverse. In the diversity of the industry. That is the best way to put it. So now if we go back to our presentation, uh, our presentation slides, let me just go back and skip these. What are the common techniques, about multi-box detection? So these are all deep learning methods, and you have the most common that are single shot detectors, where you have a backbone of VGG16 that you can see up right, and a set of convolutional layers. Then you also have the you only look once, YOLO, where you have a set of convolutional layers and a recurrent piece that is at the end, and also a faster RCNN that is uh, a backburner VGD16, and or region of interest pooling. So region of interest pooling is basically getting the regions with boxes and then dealing with these regions independently. Uh, and these are the common techniques. We're going to make a simple implementation of these elements, or let's say a simple implementation after we've talked about uh, the diverse limitations that we would have in a problem of box detection. So you want to make a contour around your image. There's a question of how do you tune the contours of the boxes. This might be done in your train set, and be sure when you label the images, because there are actually firms that label images on by hand or informatically. And you could also say that you have boxes that are not giving the exact contour of the objects, and that's bothering you when you want to make a prediction of depth or distances. This is a, a way to pass to the evolution of box detection that could be that is segmentation. And you have here the contour of the face of the cat that is detected through segmentation. That is a technique that we are going to talk about later. Then uh, we have the problem of multi-boxes, and that's our actual problem. Is how do you deal with your algorithm detecting multiple faces on one image when you design your first algorithm with a few simple layers? It is going to predict just one box per image. After that, we have a problem when the faces, for instance, are the objects or objects of the same class are too close one to the other. So in these problem, non-maximal suppression filter um, are are suppressing the second box, the closest box that doesn't have the highest probability of presence in your image. But if they are not of the same class, the problem is not the same. So we go to segmentation. What are the input formats for our algorithm? Images are layers of red, green, and blue. They're basically matrices of 256 by 256, but you could also have other types of matrices with other sizes with these three layers. What you have as an value for each of the colors of the pixels are a value between 0 and 255, 255 being black and 0 being white within these colors. You also have to restack. So you have to separate these layers, make them go through different convolution layers, and then you can restack them. And there's also a possibility to use depth-wise separable convolution layers that might also just make a mean of the three elements, knowing that this will be a grayscale output. So these elements, they actually look like that. This is our picture. And our picture is going to be divided in a grid. The grid is going to be indexed, but the problem is that in each of the pieces of the grid, it's like a little picture where we've run our algorithm or our previous algorithm. So we haven't seen the algorithm yet, but we will in the near future. And we will also have uh, the possibility to predict in each of the boxes only one box or only one centroid of the box. What we're going to predict is a centroid of a box and the width and height of the box. So if the faces are too close one to the other, they're going to be centered in the same grid cell. If they're centered in the same grid cell, they might not be detected, or just one of them might be detected. So uh, what we're going to do is create this notebook. You can follow. We're going to try to be slow, and this is an architecture that is actually pretty easy to follow. So we're going to use the TensorFlow .keras.applications, and we're going to import the EfficientNet B0. Then we're going to use the layers extension of TensorFlow.keras and import a dense layer as well as a dropout layer and a reshape layer. Then we're going to import the sequential layer. These layers are layers of neurons that we will add one after the other in order to create a neuron architecture that will give us a result at the end. For those who don't know deep learning techniques, you input your images in these layers and they return the output that you wanted because you've created a layer that has a certain number of outputs that corresponding to the output you want. Um, so if we take the efficient net B0 is going to be is an already existing and trained model. We're going to do transfer learning. We're going to not create our model from scratch, but use this backbone and include top layers in order to classify these elements that we need to classify, and as well make a regression on the vertices of our boxes. So we're going to use the include top is equal to false, meaning that we're not going to include the classification layer of the already trained model because we want to classify other types of data than what the model has been trained on. And then we're going to use an input shape 256 by 3, which is the shape of the image. Then we're going to freeze the backbone. What does it mean? We're going to freeze the weights of our algorithm. The backbone that we chose, we're not going to train the weights. They're going to stay the same. So this is going to be the layer they're trainable is equal to false. The weights on the algorithm, or the parameters of our algorithm that we're going to train, are going to be in the next layers. The parameters, as we said earlier, are as, for instance, if you take a regression, yeah, you have w x plus b, and the output of your linear regression after training will be w and b. So that's the same kind of thing in deep learning techniques. After you created the architecture of neural network, so that's sequential, you will add the layers one on top of the other. Here you're going to add an efficient net, the entire backbone, and then add other layers. This layer that you will add is the reshape. We're going to just reshape the output of the efficient net being an 8 by 8 by 1280. Then we're going to reshape it to 64 and 1280, just basically putting on the same dimension the 8 by 8. Then we're going to add a dense layer 1024 with an activation that is a ReLU function. The ReLU function being the function that lets pass only the positive outcomes. And a dropout layer that is a layer that enables us to freeze the output of some of the neurons in some of the layers in order to avoid overfitting. And we're going to reproduce this until the last layer, so the output layer, that is going to be an output of 5 plus the number of classes, and I'll explain later why it's so important. Then we have to go to the parameters number to see where we have our where we have our grid appearing. At the output of our efficient net B0, we have an output of 8 by 8 by 1280. This is a design within our algorithm, and we could have designed this going into the details inside of our backbone, and this is where the grid appears. After that, we're going to reshape this and have a row for each of the grid cells. So if we go back to the grid cells here, um, this is 5 by 5, but we chose 8 by 8 because this is the configuration of our model's output in the efficient net. So that's so that's uh, model output. Okay, 8 by 8. And we're going to reshape it, meaning that we're going to have 64 stacked outputs for each of the grid cells. So each little picture will have an output saying I have an object or not, I have a centroid, I have a width and height for the vertices, for the box. And so for this one, we don't have anything. For this one either, etc., 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 etc. And then we have the first one with a picture and the second one with an object. And the final output would be the 64 by 5 elements. Why 5 elements? Or the number of classes? Because the output that you want is going to be whether you have an object or not in the image. What are the coordinates of the 4 vertices, or the x and y and width and height? What is the probability for each class for the object to be in that class? And this way, you're going to be able to first put the centroid, the width and height of the box, draw the box, and say it's penny, or it's Raj, or it's a fruit, or it's a tennis player, for instance. Um, Now, the efficient net backbone outputs 8 by 8 grid with our output, with our input that is 256 by 256. But you could have algorithms or scaling your algorithm inside of the algorithm in order to have a grid output that is fewer grid cells. In this case, the smaller the grid cell, the higher the possibility of separating uh, the objects, but the objects also have a size that should not overflow the grid cell too much. And so you imagine, for instance, that if you have a grid cell that is too small, you would have just an eye in your grid cell, and that wouldn't be able to detect a face, for instance. So if we looked at our bounding boxes, we've talked about the outputs and we need to talk about the input. For instance, in the case of cloud segmentation, we have the input that is a series of cloud pictures that you can see here with bounding boxes overlaying one on top of the other and that are labeled with a certain name of type of cloud. These elements could be uh, so we can separate the labels for images, then create the metadata that are the vertices coordinates. Then we'll create a CNN and an NN with metadata and concatenate the resultant elements and in a tensor and pass it through a softmax layer. The idea being that we're going to use both the image and the metadata associated with the label in order to create our prediction. And we're going to uh, have the same kind of output that we had in the beginning, that is the multiple output on the same image that come from probability of classes and that define a threshold to display the class. The idea of defining a threshold to display the class is that you will have a probability of having a certain probabilities of having different boxes, and if you say, okay, if I have a probability of this box being here that is above 0.5, I can show it on my map or I can show it on my picture. Otherwise, I don't show it on my picture. Uh, okay, so next, we're going to have to deal with the grid. How do we process this grid that we can see here? The grid is what we're going to predict is the tx and ty that are the transform coordinates that we have on the grid. The cx and cy are the coordinates, are the indices of our grid. H and w are things that are not going to change. They're width and height of our object and of our box also. And this box is going to be and this box can be bigger than the proper grid. The current output of the backbone that you chose for transfer learning here is efficient net v0, can be 7 by 7, 8 by 8, and it could be smaller if you designed it smaller. The tools that we're going to use for this, we're going to use tensors and we're going to use tensorflow. TensorFlow, our tensors are objects used to represent our usual floats or arrays, and they capacitate what we call parallelization in computation or distributed computation, and where variables are easily adjusted. The format is prone to managing more easily parallelization, and we have functions that are actually very close to what we know in NumPy. For those who use NumPy, our tensors are like our tensors, for instance, NumPy. Our tensors can have an analogy to NumPy functions. np.zeros could be tf.zeros, np.I, tf.I, np.random.uniform can be tf.random.uniform. These elements are constructed differently, but they represent the same kind of data. The idea is that TensorFlow is optimized to have a to diminish the amount of computation and the time of computation. So we're going to use the variables and operation in the library for coding the grid. now we're going to see how we implement the algorithm on the grid. We're going to define a function called generate YOLO grid with a G parameter that is the output shape of our grid. We're going to create a CX that is the we're going to look that is the tile for the X direction, and the CY that is the tile index for the Y direction. We're going to take things from the least abstract to the most abstract. What is going to happen? TF.range of G is a range of integers from 0 to G minus 1. Then we're going to tie them with a G parameter, meaning we're going to create a matrix of J lines of these J integers. Then we're going to reshape this in 1JJ that is going to be adding a dimension. So maybe exactly putting the bracket around our G list of G elements. And then we're going to use this and cast it as floats and transpose it in order to have the CY. So for instance, what is transposing? If you have the input here and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you have 1, you change the position of the 2 and 4, and the 2 here you have 4 and 2, here you have 2 and 4, here you have 7 and 3, here you have 3 and 7, and that is the operation of transposition. And our grid, cgrid, we're calling our cgrid from the function generate YOLO grid with the output shape that is the output shape from the efficient net layer of the efficient net backbone layer. Then we're going to process X and Y. So the X and Y is going to be our target, for instance. So if we take our target is between -1 and 1. And we're going to divide. So that's basically our simple operations in order to normalize our elements, but also put them back in the coordinates of the grid. So we'll have y true plus 1 divided by 2 plus the C grid. So that's a normalized y true, or let's say a y true that is resettled between 0 and 1. Then we add the C grid, and then we divide by the output shape in order to normalize. Why if we're adding the C grid, I'll show you what the C grid looks like just right before this. After that, sorry. I think today is a day for me where I have I'm sorry, I'm just going to do this live. My daughter has a book that is called Mr. Melimelo, and this person is always saying the contrary of the thing that he wants to say, and I'm just doing that, but I'll stop doing this. And then you have a Y true that is WH. And we have a Y true here where we stay with the same W and H because we don't want to normalize them because it's the absolute width and heights, and there is no relativity in the width and heights, but there is a relativity in the sorry about that. I'm having a uh, okay. Um, a charging issue, which is resolved now. So there is a relativity only in the x and y coordinates of the centroid. So now there is a y true conf that is the probability of having an object or not in the grid element. So if we want to look at what the tensor looks like, it's actually a NumPy array where you have 0, 0, 1, 0, 2, 0, and under grid cell, this corresponds to the indexes of the grid cell 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, etc., etc. So now, if we want to convert our targets in order to get the right bounding boxes to plot on our pictures, we are going to have the y target, that is a set of zeros of the shape of the grid, plus that for each element of the grid, we're going to have four outputs: the presence of the object and the two vertices, or the two coordinates, and width and height. Then we're going to create the indexes of the elements that are in the bounding boxes that were predicted. Or that were in our target shape of the data set, or target of the data set. So we're going to have the index here that is going to be our normalized coordinate times the output shape of our bounding boxes, and we'll have the index of x and the index of y. And for each of the targets, for each of the indexes that come out of our bounding boxes, we'll have the probability of presence, because if the bounding box exists, it means that there is an object, so 1. And then we'll create the coordinates by normalizing the coordinates, and then we'll keep the w and h, and that's our target converted for our training the algorithm. So we come back to this after that. And no, we won't come back to this after that, because this is this is uh, going back for you to see uh, that each of these elements, so each of the grid cells here and here and here, will have the 5 elements, or the 5 output necessary for prediction. Here it is. Okay, and so what about the predicting the boxes? So here we have our y, that is our output of the algorithm, and we're going to process it, meaning getting these processed outputs that we have right before. Sorry, that we have in this function here. So the y true conf and the true x and y and the true w and h, and we're going to get in the result here b boxes where you take the first column that is superior to a threshold, meaning we're selecting these b boxes for which the confidence of having an object is superior to the threshold that we decided to take. And then we display our objects. Now that we've done this, we need to compile our algorithm and use it. What do? We create a loss function that is associated with our problem. This loss function will be a linear combination of diverse error or loss functions that will be uh, that will be associated with the presence of having an object, the localization of the object, and the class of the object. For the and each of these will have a specific weight according to what is the problematic that you want to solve. Whether you want a very accurate element on the centroid, or if you want a very accurate element on the class, for instance, you will put weights that are different. And then, for instance, I would say that in car detection for self-driving cars, localization is more important than class. If you want a counter for the number of cars that you have in a certain warehouse, for instance, the class is more important than the localization of the bounding box. So if you take the object error or the object loss function, you will have the probability of having the object times an indicator of whether you have the object, and then you put a weight on not having the object on the picture, and the error on the probability of having the object. So that's the real probability and the prediction probability square error of having not having the object. Then you have the localization. Here you have an issue that you can also solve by putting weights on these different elements of the loss function of the localization. For instance, you have here you have the x and y error, and you could put a different weight on the w and h error, saying I'd rather have an accuracy on the centroid than on the width and height of the object, because it doesn't really matter. I just want to know where the object is approximately. Or let's say, no, I want to know where the object is exactly, but I don't care about its extension on the about his extension on the map or on the picture. And then you have the L class. The L class being uh, the error made on the prediction of the class. Okay, now we're going to talk about sizing. We've implemented our algorithm. We've seen how to implement it with the grid and a transfer learning algorithm. We know what are the loss functions and the difficulties we encounter with the different inputs and outputs. We see that we can have, for instance, data sets. We can see that we have data sets that might be of several hundreds of gigabytes, as images are 256 by 256 by 3 elements. You have to know how to deal with loading the entire data set and parallelize computation. So should we reduce the amount of data, or is there another way to do that? There's another way. It's called generators, and these generators are actually creating mini batches that they will feed to the algorithm in order to and then discard after the computation is made. We can also use parallelization tools such as TensorFlow, and we can also use GPUs and Torch, such as and Torch with so Torch, that's a module or a tool with CUDA, NVIDIA being a processor, CUDA being cores where you have thread blocks and warps that create these threads or these parallelization of computation. These are all technologies that I suggest that you try and know and apprehend if you're data scientist. And I think this might be the subject of my next data atelier. So how do generator work? Data generator, you can create a custom data generator and take as input your training image path. And if you iterate on this generator, each time you iterate on your generator, you will get the next batch. So how is this working in machine learning? Here you have your model that is a CNN. You have all these layers with different neurons and weights on your neurons. And then you have a result of classification of whether this is a dog or not. You, for each of the batches that you feed here inside of your algorithm in order to make the predictions, you have a result for each of the records in your batch. This part will be able to compute a loss function associated with your prediction. With this loss function, with the chain rule, and also a process of back propagation, meaning that through the network going from one layer to the other, back propagating, we're going to update the weights associated with our neurons. And what is going to happen? Uh, we were talking about generators, and generators um, will be able to feed one batch after the other inside of our algorithm that is training, because this is how the algorithms are training, by batches and epochs through the entire data set. And we will discard the batch that we've just used in order to feed it with the next batch. So we don't have in memory all the batches all the time. We don't have a temp file with all our pictures, for instance, that is fed into the algorithm. And I also wanted to talk about learning rate and gradient descent, because The process of backpropagation is made through what we call an optimizer, that is gradient descent, and we use a certain learning rate that enables us to create a fast or slow way to update the weights throughout our computation. Uh, I have a question here. Are weights updated after each batch processing? Yes, they are, sir. Uh, and 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 also after each epoch. So what is the generator? The generator is if you take the concept of the generator, it's a simple function. We have my generator, where you have I is equal to 40 instantiated, and yi is inferior or equal to 56. We're going to add 2 to I and yield your I. So when you're going to call your generator, so next, for instance, next my generator, we actually have instantiated gen is equal to my generator. We're going to have a call, and we're going to get a 42. If we call the next generator again, we're going to have 44. And each time we're going to get to call the generator, we're going to add 2. So that is basically, if you see this as a batch issue as well, not with only I integer, but with the different batches of your data set, each time you iterate, you next on your iterating the generator, you're going to get the next batch. And you can also shuffle throughout the getting the elements of the batches. So you have, for instance, same records that might appear sometime. Uh, so here we have a generator, that the function of a generator for batches x and y. We have batch phase that is equal to integer of batch size times ratio, because we have at the same time images with objects and images without objects. Why this is true? We're going to iterate on our dataset train, and we're going to do for each of the batches length. So that's length of the dataset minus the batch phase, and of length batch phase. So that's for each batch phase size. We're going to load the face images with the size batch face. So data X and data Y is equal to next iterator image. And then we're going to have no objects and Y no objects. So that's basically a sample data of the no objects images that we're going to concatenate to our data. And we're going to yield data X and data Y. And we're going to instantiate the generator X train path, Y train, which is going to be our generator for the images. Now, how do we use the generator in fitting our problem or fitting our model? Is model.fitGenerator of the generator with a certain number of other parameters, but that's basically how we do this. I was wondering whether the weights. Um, Actually, wait. So uh, now that we've seen this, we can try to create our data generator from scratch. How do we create our data generator from scratch, and why is it important? If you want to generate images, you can use the image data generator, that is a function that is already existent for images. But if you have a multimodal classification problem with text and image data, you can try to create your own data generator. So for instance, here, if you have a data generator, you're going to create a, actually, I have a question that I will not answer in here because this might be the specific question for another workshop. And there is a init function that is going to define the diverse attributes that we're going to have, or parameters that we're going to have for our data generator. So the batch size, what is the data frame, for instance, what is the number of classes, whether we can shuffle it or not, and on epoch end, that is a function that will enable the shuffling or an action at the end of our epoch. Then we're going to create the get data function. So the get item function is going to create batches with the size of the batch that we decided. And the get data function is going to get the data of the batches with a certain logic. Here we put x is equal to logic, y is equal to logic, and return these elements. If we look, so I'm not sure you guys can see this, so there might be a way of us zooming in. I'm not so sure. So we're going to do that very simply on our other slides. On our other slides here. So that is where we're going. If you guys can see this, or maybe not, maybe you can see this better like this. This is the get data for another custom data generator. We have the same kind of functions here, and we have also the get data where we define the logic of getting the data. And we're going to get the data from a function called get input that is going to get the x min, y min, w, and h of our bounding boxes and process the image, so load the image from our path and get the image resized with these bounding boxes. So taking just the element that is inside the bounding box. And then the y, so getting the output of our batches, that is right here, just two categorical of our classification elements. And I will go back to our slides here. So that's how we could actually create a custom data generator. So now now that what you've seen is how we use it in general issues, how we use it in the industry with specific firms, how to create an algorithm of multi-box detection, how to deal with the data and the grid inside of this algorithm, and also how to create custom functions that would enable us to use the whole data sets that we have in order to train our data. Which is actually a very useful set of things to know. Now we're going to go through the evolution. So we're not going to talk so much about coding, but what are the other options that we have in order to make object detections. Here we have polygon annotation. We can follow workers, tennis players, and have contours around our players. We could have a 3D representation of our boxes. This is a 3D cuboid. And we have the famous segmentation. So you have several segmentation possibilities or types of segmentations. And the idea is when you might want contours on your objects. You have the semantic segmentation that takes each of the pixel as a category. Sorry, that takes each of the pixel and gives an output for each of the pixel within a category. This is the first image that you can see here. Each of the pixel is colored in a specific category. And then you have an instance segmentation that assigns unique labels to each instance of an object. And you can see here that not the non-represented classes are not on the picture, but the colored areas are the represented classes, or the classes that we have in our data set. So for instance, here a chair with the percentage of confidence, a person whose name is Dora, for instance, and not Dory, and also a panoptic uh, a panoptic segmentation that is a mix of both, that you can see here, where you have labels for most of the items, and some of the items don't, but still have a specific segmentation. As you can see here, there's a layer of colors that is put on top of your image, and each of the pixels has a value in your RGB layers. So that means that you have a lot of data as output. Um, and depending on how, and you'll see what we do, we can reduce this amount of data. So the differences in memory and computing costs is that detection requires fewer parameters for classes and B boxes, and image segmentation is more complex because we have a classifying each pixel in an image into specific object or classes or regions. So that is an example of the algorithms that we use in order to make these segmentation: the UNet, the MaskR CNN, and DeepLab. And here is an implementation of the MaskR CNN. So we import our packages, we charge the data, and then we use, this is all pre-trained models, mask crnn, resnet 50 fpn, and we have a certain number of objects and the background, so that's why we have 91 classes. And we create ROI. So ROI are region of interest boxes from the features, and then we make a mask predictor, mask RCNN predictor for in-feature masks. Then we train the model with a device that is a CUDA device, and that is what we talked about earlier, is whether you have a CUDA GPU or a CPU, you're going to be using this as fostering your computation. And then for each of the batches, you're going to train your model. No, to load your, you're going to, you're going to load your models. You're going to load your batches, and then you're going to make a prediction after having trained your algorithm. This uses a technology that is called the transformer neural network. That's a novel architecture, and it aims to solve sequence to sequence tasks with handling long range dependency with ease. So why do we need long range dependencies? In text issues, for instance, if you have a word and you want to make a prediction on, or a context and you want to make a prediction on the word, sometimes the entire set of the article has patches that is far away inside the sentences, so like so much above the much above in the lines where your word is, and you still need this context in order to predict your your word or your context, and or your word. And this might also be the case for a picture. Imagine you have a context of veterinary medical documents. So some of the context that is either the entire context or a part of the context might be used but far away inside of your algorithm. So that's long range dependency. And in your picture, you could have a big picture that is a picture of a park, for instance, and where objects that are far away, or textures that are far away inside of your picture or of your context, might be useful in order to create your prediction. Okay, so that's a basic introduction. And if we look at the sizes that we're dealing with, object detection is a size, is the where you have the input that is the size of the image and has 4 vertices and labels, and the output that is 8 by 8. so that's the size of the grid, 1 element for the presence, and 4 elements for vertices, and n classes if we have classification. In segmentation, you have the input that is the size of the image and the label for each of the pixels. So that's 4 against all the pixels. And this increases also the number of parameters in your algorithms. And the output is the same number of pixels than your image in mask format. So that's actually much more data. How do you deal with compressing these data? You do encoding, and we have to decode afterwards. Encoding is, for instance, you have a path of an image that is 256, 256 by 3. And we have an encoding of a mask where you have a specific region of your image that is labeled for cloud segmentation, for instance, where you don't have boxes anymore, but you have a surface. What you do is you squeeze your image, you create a line of, or a list of 256 by 256 by 3. Uh, it's approximately 2000 elements of data. And for each of these elements, you create an encoding. So not for each of these elements, but for the elements that are in the mask, you create an encoding. So if you take the data at the number 29102, you have then the 12 next pixels that are going to be in the mask. And then if you take the element 2000, no, 29,346, you have 24 pixels that are in the mask as well. And then you can try to create a mask on your data, taking, for instance, the image and putting the mask pixels as a black element, so 255. Now, what about the boxes to mask and vice versa? It's just a review. Sometimes you need to have contours, and you can't do that with boxes. So you're going to turn to a RCNN or a mask RCNN problem, and you have to convert the boxes of your input into masks. There is a size problem that is erasing, but that we've already talked about earlier. So now you can use packages that exist in order to make these conversions that are actually very simple to use. Here, for instance, you can translate polygons into masks with the supervision package. You can also create um, polygons to boxes here, and polygons to boxes, and boxes, and important. So that's importing our boxes and putting the polygons to boxes and our polygons to mask as well. But you could also use TensorFlow and PyTorch include embedded tools. So now if we look at the examples of uses of segmentation that are more prone to use segmentation than object detection, you have sometimes self-driving cars, but also medical imagery. When you can see the contours of the bones, you can see the extension or the surface of a fracture, or you can see different elements of a brain scan, an edema, a tumor, etc., etc. And if you had box detection, of course, you couldn't do such a accurate work. A mask RCNN algorithm looks like this. You have a convolutional network and then region proposal network, which is the region of interest that where there is a need for converting all the proposals to fixed shape as required by fully connected layers that are the dense layers, for those who know these simple layers. And there's so these simple layers, the dense layers, are the first type of layers that you have in your algorithms. These dense layers are neurons that just make pass your inputs through a set of linear regression, on top of which you use an activation function that is a simple activation function, such as the ReLU function, that will just let pass the output of the linear regression that is positive. These functions are the function that create the nonlinearity throughout the nonlinearity for your problem of regression or classification in deep learning. Um, so then we use the ROI and the matrices of the ROIs to make your classification for diverse elements of the pictures. Other evolutions that are not segmentation, you can do depth estimation, which is actually very important in self-driving cars. And if we remember the video that we saw earlier, it was you had a straight line that was going from the bottom of the picture to the behind of the car that is before, and it was estimating depth in order to know whether it's going to crash on the other car, which makes sense. So something else that we could use is points of interest. You can do points of interest in where you have a points of interest on bodies that are moving. You can do points of interest on objects that are moving as well. That could be, for instance, extremities, hands, elbows, feet, feet and feet. I'm singing the song. The I'm sorry, the English song Head and Shoulders, Knees and Toes. So that's knees, and that's a very good thing. And knees. And for this reason, we could also create following these important features of the body, and that could actually have a good application, for instance, for those who work in sports metrics or physiology, and that make research on bodies inside movements or sports disciplines, etc. And there is a possibility as well to follow features on the face and detect emotions. As a conclusion, you've seen applications in real life of multi-box detection. You've seen implementations and how to deal with the issues in simple issues related to size, to boxes and gridding your algorithm, and also what could be the evolutions or more accurate predictions of your objects through other types of problems or other types of algorithms such as segmentation, for instance. If you have any question now, I'll be very happy to answer. And otherwise, good luck. Go on coding, and that's it. Uh, these are actually very good questions. I think that infrared cameras might also have a specific kind of texture and colors, and that if you make these, if you turn on, for instance, the pool of training sets that you have in your algorithm for night issues, this might be how you deal with night contours for self-driving cars. How do you manage non-living objects that can be hidden in the environment of the car? So I'm actually I would love to understand better this question, because if they're hidden and non-living, they might not be moving, and so not really much a threat in your environment. Uh, is there? In fact, I was. Uh, I'm not sure I understand this question. In fact, I was wondering whether the weights optimization result is the same after processing n batches than after processing all samples. So if you could try to uh, make it clearer, the same after processing n batches than after processing all samples. Uh, I'm not sure I understand this question for real. Um, so that's it. So if you now have any question, I will be happy to answer either on the chat, or by contact on a page of data scientists. Remember that we have training in data analysis, data science, and deep learning, as well as other disciplines around data, and that will be happy to count you in uh, our uh, our our, uh, our trainings. There's also a way for you to see this video again. Also a way for you to see this video again in the data scientist page on YouTube, and other videos that are also very interesting on diverse issues of data science and data analysis and deep learning. Thank you very much for listening, and I wish you a very great day.